Okay, so last time we talked about the origin of the solar system, and we were wondering, how long it would take, 10 million years, 50 million years, millions of years kind of time frame. We said that one of the lines of evidence for the origin of the solar system was that all the meteorites had the same age, 4.5 billion years. And so when did the Big Bang happen? 13.7 billion years ago. When was the last glacial maximum? 17,000 years ago. We bandy time around. How do we know what the time scale is? How can we actually really know? Where do these times come from? And can we wrap our mind around them? Can we wrap our mind around millions and billions of years? So that's what we're going to go after today. We're going to first talk about sort of common sense approaches to time, and that's geology. And then we're going to talk about absolute time, really measuring it. And that's going to be using radioactive clocks. And then we'll talk about how do we wrap our minds around time. How do we wrap our minds around it to really know what time is involved? So we're going to start with the geology, and this is a picture which is the frontispiece of the book, and that's rocks with geologists looking at the rocks and trying to figure out how they formed. And of course, one of the things that you want to know when you look at something is when did this happen and how long did it take? And those are not so easy. When you go out and look at a rock, how can you tell when it formed? And if you look at a big series of rocks like in the Grand Canyon, how long did it take to form those rocks? Or how long did it take to cut the Grand Canyon? We'd like to be able to know all those things. And people have been thinking about that since Aristotle. Aristotle was not a very good geologist, though he was good at many other things. And modern geology sort of started in the 17th century with a fellow named Steno, who proposed two rules. One is the principle of superposition, and the other is original horizontality. Okay, so you have a lake or an ocean, and you drop sediment in from the wind or from rivers coming in, and the little particles of sediment go down and fall on the bottom of the ocean. And when they fall down, they make a horizontal layer. And it might be slightly tilted, but more or less horizontal. So when layers are formed, they first form horizontally. And then if you form another layer on top of it, and then a third layer on top of that, the time is changing progressively upwards. That's the oldest layer. That's the next oldest. That's the next oldest. And so that's the principle of superposition, that the layers on top are younger, that is more recent, than the layers on the bottom. So when you look at a series of horizontal rocks like this, you can say, okay, you can see little tiny faults in there where they've been offset a little bit from one another. These are little faults. But apart from that, you can see there's a little fault right there. But they're pretty flat, and these are the oldest, and those are the youngest. We don't really know how long a time separates those, but we know that these rocks formed before those rocks because these rocks were laid down in horizontal layers, and the other rocks were laid down on top of them. So simple, common sense kinds of principles. And then we can go to some place like the Grand Canyon, and now, how many of you have been to the Grand Canyon? A few? It's really great. You should really go. I went for the first time last year, and my partner, for my Christmas present, got me a seat in a helicopter flying around in the Grand Canyon and looking at all the layers. It's absolutely wonderful. And you can see these horizontal layers in there. And you can say, okay, these are the youngest, And then as we go down, these are the next oldest, and we go down and down and down and down. And we're getting progressively further back in time. And once we get to the bottom of the Grand Canyon, we'd have gone down a whole bunch of layers, and we'd be looking at a whole big long series of time that we don't necessarily know how long it was. But if you look at this carefully, you'll notice down here there are layers. Do you see them? And they're slanted. They're not the same as these layers up here that are horizontal. So these layers come up, they come up, come up, come up, come up, and then they hit the bottom of these horizontal layers. And this red thing that just looks like, it doesn't necessarily look like a layer because it's eroded and it has, just sand on top of it. But this red thing is a layer, and it goes up like this and bangs into these horizontal layers up here. You can see these horizontal layers down here also. They're going to go in and they're going to go up and bang against them. So we've got a situation where you have some layers that are coming up like this, and overlying them on top is a whole series of layers like that. So you look at something like that, spectacularly displayed here in the Grand Canyon, and you say, all right, well, this is clearly some kind of boundary. And how might that boundary have happened? And when you don't have one layer lying evenly on top of another, you give a name to it, and it's called an unconformity. The layers on top do not conform in their slope to the layers on the bottom. So how could something like that have happened? Well, you take your original layers, and then you rotate them through tectonic, some kind of plate tectonic activity. So you end up with your layers, lost my orange chalk, that have been sloped because of something that's happened to them. And then you erode them. And when you erode them, that means you brought them above sea level and eroded them, and now you have an erosional surface. And then they subside below sea level again, and a whole series of layers go on top of them. So these layers formed originally horizontal from Steenhuis principles, and this is the oldest and that's the youngest. And then there's an unknown time interval when they came up above sea level. No more layers were being deposited. Instead, they were just being eroded by the wind and the rain. We don't know how much was eroded, but we know that there's some interval of time here which is not determinable. Could be very long, could be less long, but it has to be long enough for those layers to become tilted and then subsequently eroded. So, for example, here we have a continental margin, and you're laying down new layers on top of this. But there was a tectonic event previously. This was a previous continental margin, but it raised above sea level and got eroded and then went below sea level again, and these things started being laying on top of it. So does that make sense? Does that happen? Well, today, Florida is above sea level and is being eroded, and Boston is above sea level, is being eroded. But 200 years from now, sea level will have risen maybe 10 meters, 30 feet. So most of Harvard will be underwater, and most of Florida will be underwater. And so having been underwater, it's now going to get new sediments laid on top of it. So an unconformity is being formed today, and is formed over the last long time interval that Boston and Florida have been above sea level. And then in 200 years, it's going to be below sea level again, and new sediments are going to start to accumulate horizontally. And then maybe 30,000 years from now, a new ice age will come along, and the new ice age may lower sea level by 200 feet. And then all that stuff that's above sea level today, that's below sea level today, will be exposed, and it will be eroded, and rivers will run through it, and then sea level will rise again. And so you can have this oscillating series of events. And of course, you can also have big mountain ranges built, like the Himalayas, causing things to be uplifted for very long periods of time. Okay, so here's another example of an unconformity. In this case, you can't really see layers in the rocks below because they've gone down so deeply in the earth that all the layers have been destroyed. And so they've gone down to great depths and been solidified and recrystallized, destroying all the layers, and then they were raised up above sea level and new layers came down on top of them. So we can get some estimates of time for the horizontal layers on top, but this is sort of a vast unknown portion. Another thing that can create an interesting unconformity is if you have a whole series of horizontal layers. So you start out with layers like this, and then you have plate tectonics happening, and plate tectonics might squeeze the layers and deform them, and so they could be formed into little folds like this because they're being compressed, just like you can do with chocolate fudge ice cream, you know. You fold it around, you get those. You erode it, and then you have a new layer or new erosional surface here, and then you can lay down other things on top of it, creating an unconformity. So the geologists are very interested in this and try to figure out the overall series of time sequences. So if you look at this series and you look at those letters, A, B, C, D, E, F, what is the sequence from youngest, that is most recent, to oldest? Okay, so there can be a confusion with youngest. Like when we say when we were young, like I say when I was young, when I was 25. You guys say when I was young, when you were 2 or when you were 4. You use young to refer to the beginning. But in geology, youngest refers to the most recent. So the youngest rocks are the ones that formed most recently. It's a kind of a different way of thinking about things. We're looking backwards in time rather than looking forward through times. So as we go from the geologically youngest to oldest, what's the sequence of letters? Here's the sequence of age. All right. To estimate how long things go, we can observe today how quickly layers form. And if you go to the ocean today, you can deploy sediment traps, put them in the ocean, measure how quickly the sediment is accumulating, and it's accumulating about 1 centimeter per 1,000 years. Incredibly slowly out in the middle of the ocean. It accumulates much faster than that, of course, near a river or something. So that means 1 meter is 100,000 years, and 1 kilometer, holy cow, that's 100 million years. The Grand Canyon is several kilometers deep. Almost 2 kilometers deep. So if you were just filling the layers of the Grand Canyon at the rates at which layers are forming as we can observe today, you'd be talking about a couple 100 million years of history. And that doesn't take into account the fact that there are unconformities, which means there are gaps in the time. So there's at least that long a time and then an unknown gap that would increase the amount. And there's another unconformity at the bottom of the Grand Canyon, an unconformity more like this. The rock underneath it, which doesn't have recognizable layers like this, is called the Vishnu schist. It's this heavy black rock that lies at the bottom of the Grand Canyon. And then layers form on top of that, and then there's another unconformity and layers form on top of that. And so there's some vast length of time, substantially greater than a couple 100 million years, that we're observing in this one place. But this is just one place. How can we compare this one place to places in Europe, or places in Asia, or places in Africa? We can look at time and recognize we're dealing with hundreds of millions of years in individual places, but how can we compare time more globally? So we can determine these sort of relative time from an outcrop, calling the Grand Canyon a huge outcrop. And we can carefully map it from outcrop to outcrop also. So we can compare the Grand Canyon to other canyons, say, in the western United States, and see if we can relate the sequence of layers in one to the sequence of layers in the other. But how can we compare that to the Appalachians, or even on the other coast? So by looking at these rocks carefully, the geologists found that in some of them there were fossils. And this is a particular kind of fossil which is characteristic of about 500 million years ago, called a trilobite. It's just one of many different kinds of fossils. And in looking at the sequence of layers, geologists, by carefully describing the fossils, found that the identity of the fossils changed depending where you were in the stratigraphic sequence. In the oldest rocks, there were no fossils. None. But then when you went up, you crossed a certain boundary, and you got the first fossils appearing that looked like this. But then, if you went up another few hundred meters, these disappeared. No more trilobites anywhere. And instead, you would start to see other kinds of fossils, like fish. But they were ancient, kind of weird-looking fish, not like modern fish. And so you would go up and you'd see this progressive change in fossil assemblage through time. And then for the first time, you'd find dinosaurs. And then the dinosaurs would all disappear, and you started to find mammals. And so if you picked up a rock and you found mammal bones in it, you would know just by looking at the rock, without any looking at the stratigraphy or anything, just by holding the rock in your hand, you would know, oh, that's one of these young rocks, because it has mammals in it. And if you picked up a rock with trilobites, you'd say, oh, that rock is from the bottom of the stratigraphic section. I know that that rock is much older than the rock in my hand with a mammal in it. So in this way, they could gradually build up a sequence. They go in one place, and they look at the layers, and they look at the fossils in the layers, and they see this layer has these particular kinds of fossils. That's a trilobite. And then they can find that if they go to another canyon or even another place on the Earth, they'll find those same fossils in another layer. And then they can go up further and they find younger fossils that were not even present in this section. But they can start stacking this on top of that. And then they have another layer that joins those two together, and they found things going up like that. And gradually, in that way, you can build up the whole sequence around the world. And this creates a global stratigraphic column based on fossils. So now you're no longer limited to just looking at what the Grand Canyon is, because you can relate the Grand Canyon to places in Africa and Asia and Europe and Australia, and you find the fossil assemblages are similar in the different places, and so you can gradually build up this overall sequence that applies all over the world. And then you can give names and say, all right, we're going to call all the layers that have these kinds of fossils in them, we're going to group them and give them a name. And then there's going to be a boundary where these guys disappear and other guys reappear, and we'll create a boundary based on that disappearance, and we'll give it another name. Okay. And in this way, the geological time scale is built up. It's divisions in the worldwide stratigraphic column based on the variations in the fossils that are found in the different layers. Okay, it's 100 years of work. It's still ongoing. And you assign names to these things, and eventually when you had radioactive dating, you can assign times. That's where the numbers come from on this scale. And so this is, of course, a fun thing to memorize if you're into memorizing things, but of course I wouldn't require that for you. And here you have the recent Earth, 0, and you go back in time, and they're minor boundaries like these things, which are 10 or 20 million years. This is in millions of years. And then you have a larger boundary. This is the Cenozoic, which goes back to about 80 million years, around 65 million years. And now this whole period, which we have a lot of detail in because it's recent, gets compressed into this little section right here. And then you go back further in time, and you have this other large interval called the Mesozoic. And then you go back further in time, and you have the Paleozoic. And then at this boundary, you reach the point where there are no more fossils. 543 million years ago, it turns out. Now, this whole section is going to then get compressed into this little section up here, 543 million years. And then you go back to the non-fossiliferous time, where we lose a lot of the temporal resolution because we don't have the fossils to allow us to correlate everything. But you can date those radioactively, and you go back to the beginning of the Earth, 4.56 billion years ago. So most geology, until recently, has been done on this interval where you have all the fossils, because that allows you to do so much more. You can correlate things very, very well. Okay, and it's often presented like this, vertically. So here we have the Precambrian that's extending to 543 million years, and then you have all these periods built on top of it, and they have epochs and so on. All right, so it's a little hard to fathom this millions of years, thousands of years. It's a little hard to fathom even hundreds of years sometimes. So I thought we would try an experiment. So here's a roll of Scott tissue paper. It has 1,000 sheets. The average American goes through 3 rolls like this a week. The average European, about 1/10 as much. Why is it Americans use so much more toilet paper than everybody else in the world? Okay, and not part of the course, just a very curious observation that I just learned this morning. All right, so this is 1,000 sheets. So every one of these squares is 4.5 million years. Okay, that's a long time. So instead of that, we'll say, all right, we're going to make 4.5 million years out of these rolls of toilet paper. These are 2-ply, so there's 450 of these. So now these 2 rolls together are going to make 4.5 million years, and that means we'd need 2,000 of these rolls to reflect this roll of all of geological time. And each one of these squares is 10,000 years. Okay, so here we are. 10,000 years ago, that's the beginning of human civilization. Okay. 20,000 years ago, that's the peak of the last ice age. 40,000 years ago, that's the end of the Neanderthals. And we go out to 20 of these, which is about here. Will you take this? And that's when human beings first appear. And just walk up to the top of the stairs. Go ahead. So we're gradually going back in time. And as we gradually unroll the whole toilet roll, we're going back 2.25 million years. I'll go over here. Sorry. We're still only about 1 million years ago. That's almost nothing, right? Will you hold on to this, please? Okay. And I haven't gotten to do this since high school. Okay, Peter, will you hold on to that? All right, that's 2.5 million years of time. And we're going to have to do that 2,000 times. I'm not sure we have time. So we want to go back 4.5 million years, because that's going to indicate one of these guys. Hold that. Okay, so we're still in the very recent geological past, okay? As we go back in this time, will you grab? Now we're still in the Ice Age cycles, and you can leave that there and just keep walking with that down. Now the Ice Age cycles are beginning. Still, it's modern life on Earth. You can just wrap around his head, that's fine. Okay, there we go. 4.5 million years. Now we need to do that 1,000 times to go back in Earth history. Okay, but we don't have time and it would make too big a mess. So now we're going to say that all the toilet paper that we just unrolled is 1 square of this roll. It's a giant Scott tissue roll, 1,000 sheets. So it goes back 4.5 billion years. Here we go. This is more fragile because it's 1 ply. So, will you hold on to that? We should go into the middle at some point. Lars, maybe you can. Can I throw this down to you guys? You can toss it around the room. Okay, we're back about 500 million years ago. That's the first fossils. And we're back in the... Sorry, you're really getting the worst of it. You can toss it to somebody. Geological time is really long. Okay? So, you know, when we were doing that first roll, that first sheet was all of human civilization. And then we had to go all over the room just to go back 4.5 million years. And that's just 1 sheet of the 4.5 billion years of geological time. Geological time is unimaginably long. So it's hard for us to fathom it, and it's what makes things that seem impossible to us or to the ordinary person, like evolution, that seems impossible because it's so hard for us to fathom geological time. It's hard for us to fathom 1,000 years, much less 10,000 years, which was 1 sheet of the first roll. And yet geological time is going back 4.5 billion years. We can't fathom it. We can't feel it. We can't taste it. Getting back about 3.5 billion years ago now, life just formed. And now we're getting back to the Hadean period. This is the early history of the Earth. And now we're at the oldest rocks. And then we get to the part of universal history that is recorded in the moon and not recorded on the Earth. And we're keeping going. Even going at 4.5 million years per sheet, it's taking us a very long time to unravel Earth history. God, this thing is like infinite. Here we go. That's beautiful. Okay, maybe you can try see if you can gather it together. So the question is, how do we know this age? We had the geologists who were estimating, who came up with the estimate that the world is billions of years old. And that seemed ridiculous to most people. And in particular, it seemed ridiculous to physicists because they said, well, we can actually do a very quantitative calculation of this. Here, I'll take it. Don't, no. Thank you. Yes, just remember each time you're using toilet paper from now on that each sheet is 4.5 million years of Earth history. The physicists said, okay, we know the diameter of the Earth and we can calculate the sphere. We know the amount of heat that's coming out of the Earth today, not from the sun, but from the Earth's internal heat. And we can say, okay, if it was initially molten, we can melt a rock and determine what its temperature was. And then we can calculate how long it would take to go from a molten state to the state of it being as cold as it is today. And they came up with 30 million years. And then they didn't know about radioactivity, but they thought they could do the same thing for the sun. The sun was much, much bigger, so it would be much harder for it to lose its heat. But the sun is also much, much hotter. And they did the sun calculation, and they came up with 30 million years, roughly. And so they said, okay, confirmation, the Earth, it's impossible, it's physically impossible for the Earth to be any more than 30 million years old. And this was proposed by Lord Kelvin, the greatest physicist of his time. And so whenever you see any scientist say, you know, something is impossible, when the other side is arguing on the basis of straightforward observations, you know, the geologists, I'm sure, were not as quantitative or mathematically inclined as Lord Kelvin, but nonetheless, they did have all their evidence on how long things take, and there was this disconnect. And so there was a big battle, and the physicists were a bit arrogant because, after all, they were using heat diffusion equation and could argue that the geologists were simply wrong. Lord Kelvin, to his credit, at the end of his paper said, unless there is some other mechanism of heat that we do not yet understand. Good for him. So this was a big controversy for 50 years. And was ultimately resolved by the discovery of radioactivity. So radioactivity allowed it to add numbers to the stratigraphic column. And that's what I just said. And so at the end of the 20th century, radioactivity was discovered. Marie Curie is the person who gave it its name. And we now understand radioactivity as being the effort of nuclides to return to the band of stability. They're out here in the red zone where they're not stable, the nuclei are not stable, and they decay back to the rainbow-colored zone in the middle where you have stable nuclei that no longer have a propensity for decay. And the way they get back there is by 3 different methods. One is beta decay, and that's when you have a neutron converting to a proton. That moves up and diagonally to 1 down, 1 up on the chart of the nuclides. You have electron capture, which is a proton converting to a neutron. And here potassium-40, for example, is capturing an electron, converting a proton to a neutron. And so the number of protons goes down by 1, the number of neutrons goes up by 1. Or when things get too big, then there's the repulsive power is so great that they start ejecting helium nuclei. And here is uranium-238, ejecting a helium nucleus of 2 neutrons and 2 protons. So the number of protons goes down by 2 and the number of neutrons goes down by 2 for a total mass loss of 4. So with respect to this diagram, beta decay is how all these guys move up to the band of stability. Electron capture is how all those guys move down to the band of stability. And alpha decay is when you have things that are way out here and they move back down this way. Keep truncating the end of the band of stability so that it doesn't extend to higher masses. 3 types of radioactive decay, every one of which follows a similar law. So that's what I just described. So this has 2 major effects. It's a source of heat through Earth's history, and it gives us time. So the way you can understand time is through this concept of a half-life, which is the time is required for half of something to decay. So you start out with a whole bunch of radioactive atoms, and here they are in their initial time. Every open white circle is radioactive. After 1 half-life, half of them have decayed, and decay is really a bad word. It implies that it disappears or something. It should really be transforms. Radioactive decay is one element transforming to another element. It doesn't disappear, it changes its identity. And so, after 1 half-life, there you have half of the white atoms have transformed to black atoms, so you have half whites and half blacks. And then after a second half-life, the remaining white ones, half of them would decay. And so now you're left with 1/4 of the parent. We call the white ones the parent, the radioactive parent. And 3/4 of them have become daughters. That's what the parents transform to when they decay. Because this is a exponential decrease, it's 1/2 each time. You start out with one total amount of, we'll call it unit, could be 1 million, 1 billion, whatever. And after 1 half-life, half are left, 2 half-lives 1/4, 3 1/8, 4 1/16, 5 1/32. After 10 half-lives, you only have 1,000th left. So after 10 half-lives, 99.9% of all the radioactive atoms have decayed away, and you have almost nothing left. Okay, so here we are with the number of atoms, and this is the number of half-lives. And this is the radioactive parent. It's going to decay away to almost nothing. This is a logarithmic scale now. And you started out with some amount of the stable daughter, and it increases as each atom of the parent decays. And this appears to go up so little because this is a radioactive scale. Here you're going from 1 million to 2 million as all of the radioactive isotope decays away. Here it is on a linear scale. This is the number of atoms of the radioactive parent and the stable daughter. And now, because it's not logarithmic, you can see there's more corresponding. As you decay lots of these away, you grow lots of these. And as you decay less of these away, you grow many less of those. Okay, so here's a radioactive isotope which has the following abundances through time. Starts out with 10,000, and then there shows the number of atoms approximately every million years. What's the half-life? Yeah, 2 million. Because as you go from 10 million years old, 10 million to 8 million years, you drop by half. And as you went from 8 million to 6 million, you dropped by another half. And as we went down to 4 million, what would the number be? Yeah, 1250, half of 2,500. Okay, so how do we use this to determine an age? We have radioactive elements, and we can measure how fast they decay in the laboratory. And they decay to non-radioactive daughters. The rate at which this decay occurs is constant. It's based on nuclear physics. We can measure it in the laboratory. And so if we know the rate of decay, and we know the amount present of the parent and daughter, we can calculate how long this reaction has been going on. Now, stated that way, it seems pretty simple. And in your handouts, I go into the detailed mathematics of how this works. And I've put them in gray because this is for those of you who are interested in the mathematical details. But it's not something I'm going to go over or expect you to know that I went through before. So let's look at carbon-14 dating. A very important aspect of radioactive dating is that many elements, mostly even, have multiple isotopes. So carbon is an alpha particle nuclide, and the most common isotope of carbon is carbon-12, 3 times 4. It's one of the fourth most abundant element in the universe. But there are also little tiny amounts of carbon-13, much less, of course, because it's odd and it's not an alpha particle nuclide. And you also have, through cosmic rays coming in and interacting with the carbon in the atmosphere, you make very small amounts of carbon-14. They're all carbon. They're all in your bones, in your skin, all the molecules that make you up. You have all 3 isotopes of carbon. You're mostly carbon-12, but you have a little bit of carbon-13 in you, and you have carbon-14 in you as well, because you ate food, and the plants, picked up the carbon dioxide from the atmosphere, and it has radioactive carbon in it. So when you die, we'll be able to date you, because you have a carbon-14. You're very useful. So we can measure carbon-14 relative to carbon-12. And the carbon-14 has a half-life of about 5,800 years. And so when you start, you'll start with carbon-14, carbon-12 of some number. And so we're just going to normalize that number, so it's going to be a number of 1. And when you go back one half-life, you know that it's 5,800 years ago. And if you go back 2 half-lives, it's about 12,000 years ago. And 3 half-lives, it's about 18,000 years ago, and so on. And so by picking up a bone or a piece of charcoal from an archaeological site or from a fossil, you can just measure the carbon-14 to carbon-12 ratio and tell how long ago that was isolated from the atmosphere. As long as you breathe and eat, you're taking in carbon-14. You die, and the carbon-14 just starts decaying away. Now, what this requires is you have to know how it starts. And so the way that people estimated how it starts is to measure the atmosphere today and assume that the carbon-14, carbon-12 ratio of the atmosphere in the past was the same as the atmosphere today. Seem like a good assumption? Pretty good, but might be off a bit, right? So, because it might be off a bit, now when people make this measurement, they always refer to a carbon-14 age, because other estimates of dating things show that the carbon-14 age, once you go back in time, gets off by about 10%. Now, it requires that the bone or charcoal is not contaminated by interacting with the atmosphere, has had something, and it can't have lost some of its carbon. It requires that the decay rate be constant, which we think it is on the basis of nuclear physics. It's good also if you know the initial concentration of something. In the case of carbon-14, we know the initial concentration of the parent. But if we don't know the initial concentration of the parent, it's good to know the initial concentration of the daughter. So this is the parent. And if there's no daughter, for example, if carbon-14 decayed to something useful, and we could just count that and knew it was 0 at the beginning, we could just count that and determine what the age was. But it decays to nitrogen, and nitrogen is abundant in the atmosphere, and so it's useless in terms of giving us an age. So carbon-14, we're estimating the initial concentration of the parent. Other systems, you measure the amount of the... So here's carbon-14, 5730 exactly. And so that's used for dating things back to 10 half-lives. 10 half-lives is 57,000 years. Oh, dear. 57,000 years is 6 sheets of the 2-ply toilet paper. Right? And we had 2,000 rolls of the 2-ply toilet paper going all the way back in time. So this is great for archaeology or very recent climate change and so on, but is no good for rocks that are older than 57,000 years. It's only the most recent part of Earth history. If we want to go back further in time, we don't necessarily know how things were initially, and so we have to use more complex methods. And the classic method that is more complex is using something called isochron dating. And it works like this. So we've seen, by looking at the carbon-14 system, that if we know the initial concentration of the parent, we can count how much is left and get an age. Or, if the daughter isotope starts at 0, we can measure the amount of the parent that is left and the daughter that has been generated to get an age. For example, the mineral zircon contains a lot of radioactive uranium and none of the daughter element, lead. So, as a simple example, if we measure the ratio today and find equal amounts of uranium and lead, we know that 1 half-life has passed. Zircons provide the most abundant and best ancient ages. Tens of thousands of measurements have been made. But not every rock has zircons. So, how can we determine the age if we can measure the parent and daughter today, but we do not know how much of either one of them there was at the beginning? Well, what are we dating? We're dating the time of formation of the rocks or minerals from a well-mixed reservoir. For example, the solar nebula was all mixed up and homogeneous, or a magma before it crystallizes is all mixed up and homogeneous. For this special method, which we call the isochron method, we use the ratio of the radioactive daughter, call it D, to another isotope of the same element that is not produced by radioactive decay. Call it S for stable. D is produced by the decay of the radioactive isotope R. So in the initial well-mixed reservoir, the ratio of D to S is constant, and every object made from that reservoir will have the same ratio because D and S are isotopes of the same element, so they behave identically during chemical processes. But different minerals have different affinities for the elements. For example, rubidium is underneath potassium in the periodic table, so it behaves like potassium, and a potassium-rich mineral takes up a lot of the element rubidium, which happens to be radioactive. Rubidium-87 decays to strontium-87 by beta decay. Strontium is beneath calcium in the periodic table. So calcium-rich minerals have a lot of strontium and very little rubidium. 86 strontium is the non-radiogenic isotope of strontium. So when minerals or meteorites or whatever first form, they can have a variable ratio of R to S, the radioactive element to the stable daughter, to the stable element of the daughter, stable isotope of the daughter element, and identical ratios of D to S, that is the two isotope ratios of the daughter element. So we can make a diagram of D to S versus R to S, and it will look like this at the initial time. So here we have the radiogenic parent divided by the non-radiogenic isotope of the daughter element versus the two isotopes of the daughter element. These are all the same element, so they behave identically. So at the initial time, they all have the same ratio. They plotted the same value. We'll just choose a value of 0.7 in this example. But the minerals or meteorites take up different amounts of the radioactive parent. So the ratio of R to S can vary depending on what minerals happen to be involved. This is the initial state at time equals 0. Now what happens after, say, one half-life? Then half of the R isotopes have decayed, and every R isotope that is decayed has created a daughter isotope D. So if we started out with an R over S ratio of 2, half of the R's will have decayed, so that will have decayed to 1. And every one of those isotopes will have increased the D in the of the daughter element. And therefore, as this drops from 2 to 1, this will rise from 0.7 to 1.7. Or if this one drops from 1 to 0.5, it will rise from 0.7 to 1.2, because every one of the isotopes of R that decays here creates this D. Let's look at a numerical example. If we take an initial state with 3 different minerals, so now we're using the actual radioactive isotope and its radiogenic daughter. So mineral A has 1,000 rubidium-87s, 700 strontium-87s, and 1,000 strontium-86s. So it has a ratio of 87 strontium to 86 strontium of 0.7. And it has a ratio of rubidium-87 to 86 strontium of 1. So that corresponds with this point. Mineral B has twice as much rubidium, so it has a ratio of rubidium-87 to 86 strontium of 2, but of course the ratio of 87 strontium to 86 strontium is the same. And maybe there's another mineral C that has no rubidium in it at all. It has different amounts of strontium, but the same ratio. So on this diagram, we looked at one ratio with a value of 2, one with a value of 1, and one with a value of 0. What happens after one half-life? Half of the rubidium has decayed away, so there are now only 500 rubidium atoms. But all 500 of those atoms have decayed to 87 strontium, so 87 strontium has gone from 700 to 1200. In mineral B, the 2000 rubidium atoms have decayed to 1000, and the 1000 atoms that have decayed have transformed to strontium 87, which has increased to 1700. And in the third mineral with no rubidium, there's been no decay, and therefore no change in the strontium isotopes. If we look at the ratios, here they are, 1.2, 1.7, and 0.7. So just as we saw in this diagram, this one, they all start out at 0.7. The one with a value of 2 goes up to 1.7. The value with a value of 1 goes up to 1.2. Therefore, on this diagram, the slope gives us the age. If only 10% of the atoms had decayed, it would have only moved up a little bit, and you'd have a line that was fairly flat. If it were 2 half-lives, then this value of 1 would have gone all the way down to 0.5, and the line would be much steeper. The line gets steeper and steeper as time passes. An isochron is both a determination of an age, and it's a test of whether a suite of rocks or minerals formed from a homogeneous reservoir at the same time. There are many isotope systems, all of which can be used to generate isochrons. And each one of those isochrons with a different parent-daughter pair gives an independent test of the validity of the age. So, in our discussion of solar system creation, the hypothesis is that chondritic meteorites all formed from a well-mixed solar nebula at the time of formation of the solar system. If that's true, they should all plot in an isochron, and the age of the isochron is the age of the solar system. Earth, if it formed at the same time, should be on that isochron too. So, for those of you who want to go through the math, the PowerPoint the slides are here, which you can go through if you're interested. The bottom line is you generate an equation like this one, where the 8786 strontium value is equal to the initial value plus the rubidium 8786 strontium times a time term. That's y equals b plus xm. That's the equation of a straight line where the slope gives the age. So here are the data for meteorites, and you can see all these different meteorites plotting beautifully along a single isochron, and that single isochron has the age of 4.56 billion years. That supports the hypothesis that all the meteorites formed from a homogeneous, well-mixed material at the same time. And while it's more complicated to get the data for the Earth, it turns out that the Earth plots on the same isochron. There are many different methods of isotope dating, and that's because there are many different radioactive elements. And the fact that you have so many different elements means you can test it. You can construct a diagram with the rubidium-strontium system, and you can construct a diagram with all these other systems. And then you can compare them and see if the ages agree. So then we can try that with different systems. And you can use the rubidium-strontium system like we've been talking about. You find chondrites 4.56, the moon 4.51. You can use this other system, doesn't matter what those elements are, 4.55, 4.44. You can use lead, 4.56, 4.52. What do you notice? Alvin. Moon's a little younger. So the moon formed after the solar system formed. There's about 50 million years during which Earth was going around and planets were forming, and the moon formed after the Earth. It was a relatively late event. And we think that was from a late impact of a planetary object the size of Mars, which smashed into the Earth and knocked out a huge pile of debris, and that debris then ended up solidifying around Earth's orbit to form the moon. Yeah. All right, so then we need to date the Earth, and we don't have anything on the Earth that hasn't been perturbed by Earth history. And so there's a more complicated way of determining it, which I'm not going to go through. But the moon turns out the Earth turns out to have formed at the same time as the chondrites. So the age of the Earth is the same as the age of the chondrites. So let's look at the take-home points. So you just do geological reasoning, and it makes the Earth many billions of years old, but we don't know how many billions it is. And then radioactivity was a heat source for the Earth and makes us able to quantify the time scale. And the radioactive elements have different half-lives, and so they're useful for different time periods. Carbon-14 for young stuff, other systems for very old stuff. There are a lot of complex methods of dating that we don't have time to go through in detail. And an important test above them all is that they all agree with one another, and as you saw that they did. And the age of the meteorites and of the Earth, determined by these methods, turn out to be the same. So that's a length of time that's very difficult for us to fathom and makes seemingly impossible things like evolution much more possible, because this vast expanse of time is available for all these things to take place.